don't think in my schooling career have I ever seen deca and hecto.
They exist. We don't really use them.
And then,
Here's a,
yeah, more units here. We measure current in amperes or amps. Okay, so capacitance and charge are related to each other. Capacitance is measured in farads. A farad is a really big amount of capacitance. Normally, we talk in microfarads. I would say is the most common unit. Perhaps picofarads, nanofarads. Henries, that's how we measure inductance. Inductance and capacitance we haven't talked about a whole lot, but those are useful to know. Talked about hertz all last week. Ohms, that's the unit of resistance, so I would say kiloohm, megohm, really commonly used. Decibels, like we just talked about.
yep. Here we go.
Oh no, I kill it.
No, I think that's the end.
Is that the end?
Yeah.
That is the end.
Oh,
This is-
hour
this
2
is-
is done. Congrats.
This is the slimmed down version.
This is the, yeah.
There's another one you can do.
All right, yeah,
I
we're not,
figured you'd do both of them.
we're not done. But,
What?
All right.
middle circuits. Oh no.
All right. This is a semiconductor. It's a transistor. Transistors typically made of silicon, sometimes germanium. Those are two pretty common.
I think those are explained later on.
Okay.
There, okay, cool.
All right. So for here, for those of you who aren't familiar with schematics, a squiggle like that is a resistor, as opposed to, can you draw an inductor?
An inductor would be, I have to come over here. So, inductors are loopies. Sometimes they draw them like that. Whereas a resistor is jagged lines. And you'll know it when you see it. Like, hand-drawn, they look kind of similar.
There's some slides with
But they are, okay, yeah, so they're coming up. But for now, just know, it says R also. Usually they're really nice about making it make sense. Yeah.
What is a transformer drawn as?
All right.
It's going to be...
That's further in the slides also.
Okay, but you'll get pretty much
There's a
two
slide
of
for
them.
that.
There's a slide for that, yeah.
It's just
And
up against each
Two
other.
parallel lines to
And
indicate
yeah,
there's a metal core between them.
Depending on which kind you got, usually they'll have the, yeah. Some
All right, well,
simplifiers.
just to cover the basics, lines represent wires, dots represent connections, batteries are indicated by a single cell would be a long line and a shorter line. Long line is positive. The way I remember that is a plus sign has more line segments than a minus, so the minus must be the short one. Anyways,
So I think of it
whatever
that way too.
works.
It takes more ink to draw a plus sign, so the
Yeah,
longer one
well,
takes
that,
more
yeah,
ink.
exactly.
They're so new. It makes sense.
Meters are often represented by just a circle with what they're measuring inside on a single letter. So A for ammeter, V for voltmeter. This is a very simple amplifier in this case. This takes an input signal here into the base of the transistor. Emitter arrow.
Because it's emitting stuff.
Yeah, I think of it. E is a vowel. Arrow starts with a vowel too. Asynchronous don't. Whatever.
Engineers are
works.
weird.
This is an NPN transistor because this arrow is not pointing in. NPN. Yet another great way, and that I think is a test question.
Yeah, that's why I'm drawing it.
Or if it's a PNP, it points in positively. Yet another silly mnemonic, but whatever helps you to remember it. Collector's on the same side as the emitter. Base comes in to the middle, and those are the three legs of a transistor. And that's pretty much that schematic. All right, so here's, as we were just drawing the symbol for a resistor. If you can vary the resistance, it has this third leg with an arrow on it, and that just says you can move it along here, and the resistance changes between either of these two legs. Resistance does not change between these two. That will stay constant. But that, again, useful for volume control or adjustable
Yeah.
light dimming.
Yeah, pretty much any knob you see
Any
is
of those, like,
actually
yeah.
a potentiometer.
Freely rotate, probably a potentiometer. There are other things. All right, capacitor. It's funny looking capacitors.
Yeah, I don't know what that is.
I'm gonna draw a not weird capacitor. They normally just look
Yeah.
like this.
Not sure why it looks like that, but you see capacitors sometimes with just two parallel plates, sometimes with curved. Typically, if it has a curved plate, that means it's going to be polarized, which means in a circuit, it can only really fit one way. If it has two parallel lines with no plus sign, it's going to be non-polarized. But, so it kind of acts like a battery in that it stores energy. But a battery is an electrochemical reaction. A capacitor is just charge gathered on plates because they are attracted to each other, but they can't bridge the gap because there's something insulating them, and that is a capacitor. We call that insulating material a dielectric in this case. All right, inductor, again, sort of like a resistor, except and sort of like a capacitor. It's one of those weird components. It stores energy in the magnetic field around it, and when you apply a voltage initially to an inductor, there is virtually no current flowing until some amount of time later, and it starts flowing. Likewise with the capacitor, if you put voltage across it, there is a lot of current flowing, and it slowly starts dying off as it charges up. We can talk more about that.
I'm just drawing them up here so that we can see the difference between them. Because, battery and capacitor, they all look
They
kind
look
of similar.
similar. All right, transformers, as Sarah just talked about, if it has parallel lines, that means it has a metal core. If it doesn't, it just means they're close to each other in hair. The ratio of the turns allows us to keep the power the same while changing voltage and current. So if the power stays the same, if the voltage goes up, the current must go down. And we use transformers all the time to charge our phones. We've got 120 volts available at the wall, but we only need 5 volts to charge our phone. So there's a transformer in there to step it down to a reasonable voltage for
Really not fry your phone
cell phone.
in many cases.
So we just talked about units. Again, henries for inductors, farads for capacitors, ohms for resistors. All right, so let's talk about reactance. So reactance is like resistance in that it can limit the current and develop voltage across it. However, we talk about reactance for inductors and capacitors. So I was just talking how when you charge up a capacitor initially, you see a lot of current, which gradually decreases, whereas an inductor, you see very little current and gradually increases. How fast they decrease or increase is related to the reactance. All right, so when we combine resistance with reactance, we get this term called impedance, and we represent it with a capital Z. And essentially, that's going to tell us how the circuit reacts to both alternating and direct current. We'll talk more. Okay. Resonance. Wow, we're just moving right along.
That was great.
If you're in electrical engineering, pretty much this whole set of slides is an entire semester's worth of class, so that's why we're like, but we go more in depth. Like, we're not throwing a semester's worth of stuff at you right now, so don't freak out. But
All right, so resonance. When a circuit is resonating, you can essentially take out all the reactive components and are just left with the resistive components. Because essentially, capacitors are the inverse of an inductor. And at resonance, the energy in one will be transferred to the other at that resonant frequency, which means there's really no loss of energy between transferring between that capacitor and inductor. which means you can just kind of take it out of the equation altogether. The energy that's swapping between is not going to be involved anywhere else, and you're just left with any resistive component, is one way to think about it. Hopefully we've got some...
Hopefully.
Yes, okay.
Oh,
perfect.
thank you. I was about
Alright.
to draw it, so I'm glad they.
Yeah, so these look a little strange, but...
Yeah, that's
It was
a,
rendered kind of funny.
Yeah,
I'm
but
actually-
essentially we've got parallel and series LC circuits. LC, inductor, and capacitor circuits here. So they work similarly. I mean, the energy contained in here will transfer to here at the resonant frequency and vice versa. And I was talking about resonance. At resonance, this will be left out of the circuit, which means essentially there will be no current flowing through it. So we can vary the resonance if we can vary one or both of the component values. So we can have variable inductors and variable capacitors, which is exactly how you can tune a radio, because you need to change that resonant frequency in order to tune a particular station. So we want to be able to adjust that somehow. All right, semiconductors. There are semesters just on semiconductors alone.
So if you
let's
want to
see.
know more about any of these,
Yeah.
take some EE classes.
Okay, so semiconductors, we call them semiconductors because they're kind of insulators some of the time, and they're kind of conductors the other part of the time. And the way we can do that is by changing the amount of electrons in a particular area of the semiconductor. We can do that by adding, or basically adding different types of chemical elements to the semiconductor. So we can take silicon, we call this process doping. We dope it with boron or phosphorus or some other chemical, and that allows us to change the number of electrons that are freely available. And that converts our silicon into a p-type or n-type, depending on if there are more electrons n-type or fewer p-type. The opposite of an electron is called a hole. Electrons want to fill a hole, so p-type material is mostly holes, and an n-type is mostly electrons. If we combine those two together, we get a junction. And I think that's probably the next slide. We call it a p-n junction, which we also call a diode, and for whatever reason, our
yeah, the
Yeah.
pictures are messed up. I don't
all right,
know.
picture's messed up, but anyways, diode is a triangle with a line on the short side.
I don't know
And
why the line's not there, but this is
without going into any real detail on why it works, which again is a semester in and of itself, it basically allows us to only allow current to go in one direction, which is current is the flow of positive charge. So not the flow of electrons, that's the opposite. So we say the positive charge goes with the arrow. Electrons go the opposite way. And why that convention is, no one can say other than Ben Franklin thought.
some old dead guys
Yeah.
thought this was a good idea.
Yeah. So what do we use diodes for? Well, we use them a lot to convert alternating current to direct current. And essentially do that because we say current's only going to flow one way through the diode. So if you have, draw alternating and then like,
Just like that.
essentially we're going to have like a sine wave. And if we feed that through a diode, we're only going to get the top part, or we're only going to get the bottom part. And since it's going to stop conducting at 0 volts, we're going to end up with an average voltage greater than 0 volts.
So this right here, this is what it's outputting. You draw a line through.
Yeah.
So it's like positive, negative, the only part that's getting through here is the positive part.
So we just chop
You just-
off
yeah.
chop off the bottom here, and now we look at the average voltage before was 0, right? Because it's going to be sometimes positive, sometimes negative. But now we just chopped off the entire negative part going through the diode.
So now the average is up here.
average voltage has just increased. So this is very, very common, and basically any power supply that plugs into the wall.
I need more colors. I'm sorry.
Well, we have plenty up here.
All right, a transistor is what happens when you add another junction. So a diode is a two-junction or a single-junction device. A transistor is a two-junction device. So we call it a p-n junction for a diode. Well, that's why we call a transistor an NPN or a PNP, because you now can have two different orders to your transistor's junctions. So you can think of it as a switch or an amplifier, depending on how it's configured. And we have different types of transistors too, other than just NPN and PNP. There's a whole series of transistors called field effect transistors, which operate completely differently than the standard bipolar junction. To give you very brief history, field effect transistors were thought of in the 1920s, but weren't capable of being produced until the 50s. Bipolar junction and its very closely related counterpart was invented in 1948 at Bell Labs. These replaced vacuum tubes, which were very hot and very inefficient before then, invented sometime in the early 1900s. So this is why transistors revolutionized our devices, because if I had the vacuum tube equivalent of this, it would be larger than this room, and it would take up megawatts of power. But with transistors, I can manufacture them at the nanoscale and keep it in my pocket. So in the case of digital electronics, we think of transistors acting like switches. In the case of analog, typically more used as amplifiers.
Which is on the test.
Yep. All right, integrated circuits. When you combine a bunch of transistors together, you get some logical block, typically in the case of digital circuits, or maybe a different kind of amplifier in the case of analog. So here we have what's called a flip-flop. This is specifically a D flip-flop, and essentially when you clock in a pulse here, the data on the D input will appear on the Q output, and the inverse of that will appear at the Q naught. So if it has a bar over it, that means the inverse of Q. This is a differential amplifier, op-amp. Essentially, the output is going to be somehow related to the two inputs. So if the positive input is greater than the negative input, this will be positive, vice versa. So basically, integrated circuits taking a bunch of transistors, piling them all onto one part, one integrated circuit. All right. Who here has ever gone to the fuse cabinet to replace a fuse? All right.
You guys are very lucky individuals.
A
apparently never
lot of
did
the time
this.
nowadays we have breaker panels that you just have to flip the switch. But before then, you actually have to take out a fuse, stick a new one in, because there is a fusible link in there that will simply burn up when too much current goes through it. So in the case of a short circuit of, when I was 8 years old and stuck a fork in the outlet, big spark, lights in the room went off, and parents were very unhappy, but they went to the breaker panel and just reset the breaker. Well, in the case of a fuse, you would literally have to remove the fuse, stick a new one in, and you're good to go. But
Your car is still like this more than likely.
yes, most cars do not have breakers. Most cars have
Little tiny
fuses.
fuses.
Little tiny plastic one, yep. So circuit breakers, resettable, fuses, one-time protection. If you try and stick a paper clip in where a fuse goes, it'll work. I almost guarantee it'll work.
I got 16 cents out of a fuse panel.
Oh gosh. So yes,
So
you can
some
use
people use coins.
you can use coins as well.
But the
That's
problem
never
is
been a
now-
logic, but you are.
And pennies and silver dimes really conduct electricity well. You can burn down a house that way.
Yes,
Yeah.
and unfortunately, while the house is burning, the pennies will not, because they were designed for many hundreds of amps going through a penny before it will melt, whereas fuses maybe 20 amps before.
Well, the other feature is you could screw a light bulb into that same hole and use it to figure out when you found the short.
Right. So a light bulb will light up when it has current going through it. So if there is a lot of current going through something, light bulb will glow brighter. Very, very handy indeed. Unfortunately, we don't really have fuse boxes anymore so much as circuit breakers. All right. Switches. So these are real switches, not like electronic switches like a transistor. The switches on the wall in the room here are momentary push buttons like this, but you'd probably be more familiar with a standard single pole, single throw. And let's talk about switch terminology. This is the pole, okay? So if we say it has a double pole, that means it has two of them, and the dashed line indicates that they are ganged together such that when you move one, it'll move the other. And single throw indicates that it only has one contact to be made, whereas a double throw means it has two contacts that can be connected. So we would typically wire the switch up. We would have, like, say I have two sets of speakers in my living room or something, and I want to be able to power one or the other. Well, I would use probably this. In fact, I'd have my left channel and my right channel going to speaker 1, speaker 2 left, speaker 1, speaker 2 right. That way, when I switch these, the speakers will only be on speaker set 1 or speaker set 2. And push buttons are often momentary. You'll see these either advertised as normally open or normally closed in O or in C. And in the case of
Those are relays.
relays, yeah, we'll talk about relays in just a sec. This is normally open, which means contact is only made when you push it, whereas normally closed means the contact is broken when you push it. So a relay is an electronically controlled switch, just like a transistor sometimes, except these are much more rudimentary and require a lot more power to switch. But essentially, we have a coil, an electromagnet, which attracts the pole when you have current going through it. So, has anyone built an electromagnet before? Picked up paper clips or something? Same exact thing happens here. This is the paper clip, and it's going to be pulled down and shorts the common to the normally open. And if it's not energized, it will short common to the normally closed. Yes?
That was my one thing. A single pole, double throw switch, most commonly you'll find one in a house, it's a stairway switch. So once you get somebody at the bottom, somebody
Yeah, three-way or
Yeah.
two-way switch, yeah.
Yep.
And why those can work, I mean, we could draw a circuit if you wanted, but essentially it's got another wire in there that allows the switch to just toggle, yeah.
Fix it sometime.
All right, so I think that's relays. Relays, what are relays used for? We use relays a lot in, actually, the push buttons on the wall activate relays inside the light fixtures here because we can gang multiple lights together and operate. There's also, yeah, you know.
Okay, well, notably, you can hear, a lot of time relays, you can hear it click.
So all those, yeah.
It's just controlling lights too, but
Relays
you can hear
are
the,
very,
some of that's the lights turning on, but relays do make clicky noises.
relays are often used in the final output stage of a transmitter because you want to be able to switch the antenna between transmit and receive. So you want to be able to switch between the high power amplifier and the receiver. And we just have one relay that when you key down the microphone or key down your Morse code key or whatever, it's just going to automatically do that switching for you instead of having to unplug it and plug it in. That gets real old real quick.
Was that it for?
Yeah, that's it for relays.
Well,
All right, here are all these other circuit symbols that you probably should familiarize yourself with. Kind of hard to see back there,
We'll send you this sheet.
just looking at diodes alone, there's lots of different kinds of diodes.
One kind we didn't mention was light emitting diodes, LEDs.
LEDs are identified.
Are a diode, yeah.
They have a squiggly, two squiggly arrows typically, showing that they emit some Zener diodes kind of looks like a Z instead of the,
That's really. I'm trying to draw lines here. I can't draw straight lines.
kind of looks like a Z on the output. They have an interesting effect. We said diodes only allow current to go one way, except it's not entirely true. If you put enough voltage across a Zener diode, it will start conducting. That's a very useful thing because typically they break down or start conducting at a very specific voltage. So a 5.2 volt Zener diode will break down at 5.2 volts. Let's see, what else we got? I'm trying to think what would be on the exam. Yeah.
Be able to know. I was reading the exam today, and they have some where you just want to know. You don't have to know like, oh, specifically that is a dual gate N channel. Like they're not that specific, but just be able to tell a bipolar transistor from a field effect transistor.
Yep.
Which got them up there, but that's pretty much you got to recognize the symbol and just be able to say, oh, that's this or that's that.
So yeah, I said in the case of bipolar transistors, you can see if it's NPN or PNP because which way the arrow is pointing. Just looking through these, it's not always consistent depending on what kind of, in the case of a unijunction transistor or junction FET, they're not very commonly used. Don't worry yourself with them, but notice that the arrow is pointing in the opposite direction. For N channel, it's pointing into, even though we say it's not pointing in. These little bit more popular, like a lot more popular. All these, this is what your cell phone, your laptops, all your computers, they use these kind of transistors.
Those are field effect for the back. Because I know it's kind of hard to see.
We call them MOSFETs. They're metal oxide semiconductor field effect transistor. Really big name, that's what we call it, MOSFET. Or just kind of FETs.
And that's hour
all right, surely we have some questions.
please.
About the Zener diode, why would it be? What's the good thing about a Zener? You said that it could break down at a certain point, but is that ever a good thing, or is that?
That's a really good thing.
Better elucidate on breakdown.
Yeah, breakdown sounds like it's a really bad thing, and in this case, it's recoverable. Once it breaks down, if you remove the voltage, it can be used again, right? Breakdown is like, say I have a spring and I can push it over, applying enough force. The spring will pop right back. That's in the case of this diode. It'll break down in the case of, you can bend it over, but it'll pop right back.
Old English motorcycles, say Triumph, Royal Enfield, and things like that, had a great big one stuck under the headlight that was the sole voltage regulator on the motorcycle. They got hotter than a $2 pistol, and yeah. Good design? No. British? Yes.
Like, for instance, a very common circuit would be, we have some voltage source here, and maybe it's 12 volts. Maybe it's 13 volts, maybe it's 6 volts or something. We'll add a resistor here to limit our current, and then we'll have a Zener diode here. Now what's going to happen is we're going to have some predetermined Zener diode here. Let's say that 5.2 volt I was talking about earlier sounds pretty good. So this is 5.2 volt Zener. What is going to be the voltage across the Zener? It's going to be...
Oh, no, I'm sorry.
We got 12 volts across our voltage source. We've got some resistor here to limit our current. As long as this is greater than the breakdown voltage of our Zener, we're going to end up with 5.2 volts across our Zener. No matter within limits, if this is 1,000 volts, we'll kill this by other means. as long as this is greater than 5.2 volts, we're going to end up with 5.2 volts across our zener. And that's why it's useful for voltage regulation. Because it doesn't matter if that's 12 or 14 or 15 or whatever, so long as it's greater than 5.2, we'll end up with 5.2 on the output.
Any other questions? Yes.
Can we use a Zener diode for under voltage protection?
Can we use it for under voltage protection? What do you say, John? If we were to drop a...
Over voltage protection, your
Yeah.
basic crowbar,
Yeah.
so it does over voltage, but
Because what you can end up doing for over voltage protection, you could probably, this is not going, you won't have any current going through this resistor until this diode starts conducting over 5.2 volts. So if you add 4 volts here, there will be no current going through this resistor. You can use that to essentially turn on another transistor and crowbar the circuit. What we mean by crowbar is, the term comes about, we can throw a crowbar at electric circuit and just short across the outputs and draw an excessive amount of current and hopefully trip our fuse or breaker that we're connected to. So if we can somehow trick this thing into shorting the output when it overvolts, then hopefully that fuse we put in line will blow, and that's over voltage protection. Does that kind of answer your question?
Any others? We're going to send you all this stuff anyway, so don't feel like you have to ask me. All right.
What happened to hour 4?
And where's hour 4? Is this actually hour 4? It
He
labeled-
didn't think anyone was counting.
wait a minute, you got 3 and 4 with this, I sent you
2
2
and 3.
Those are the 2 presentations.
We just did 2 and 3. And now we're on 5.
Well,
We can do
stand
5.
by, I'll fix that in a second.
Okay. I mean,
While
yeah.
we're fixing this, who wants to see how the two-way light switches work? Anyone? I do. I don't like you guys. All right. So here's our mains power, which I'm just going to draw as a squiggly line. Okay. Now we've got this nice little light bulb here. Okay. And now, how are we going to turn this on? So a one-way switch is simply this, right? Got a nice little one-way switch. Okay, so when I flip this, this light's either going to be on or off. If I put another one in here, if I flip this one and this one's open, what's going to happen? It's off all the time. So long as any one of these is open, light's off. So what can we do to correct it? Right? What if we did this? Now we've got our single pole double throw, and now, no matter which you toggle, the light will always go on or off, vice versa. So here we've got one current path with both switches in the up position, and that would be on. Now it's off. Now flip the other one, and it's on. That's how that works. Now three-way switches, those are just magic. But two-way switches just need a single pole double throw times 2. One at the top of the stairs, one at the bottom of the stairs. Good to go.
Well, we're loading up hour 4 at the moment.
Do they build on each other, or are we okay?
No, they're
So
separate
we can
as
just
far as
go.
I can tell.
We can do hour 4 next time.
Okay,
or
well,
something.
you guys skip an hour.
Do Control L.
Control L, that's the secret?
What?
They broke it, actually, so.
Well, that was supposed to be screen. Oh my gosh.
Oh, it's because I need that thumb drive, actually.
You just took our file.
That's why.
Throw it.
It wasn't actually.
That was, we could join the football team, guys. That was beautiful.
Yeah. Give us a jersey. Try out.
Alright, well, I killed it, so that's great. Oh, did it come back? Oh, look at that. Nope. Okay, maybe if I kill all these.
You have to close Identity Finder at the bottom because it's trying to steer that.
No,
Yeah, just
stop
click-
it.
just hit cancel on it,
Stop it.
and then now reopen it.
No,
No, not the
Internet
Explorer.
Explorer. No.
You look like you did. Done. It's
Sit.
okay.
All right. Okay. Maybe this time.
No, it's magic.
There's okay. All right, so
Literally
we're at hour
magic.
5. You sat through 2 hours already.
Time flies when you're getting lectured.
Is there no pictures? All right, I'll zoom for a picture. Okay, so we went over a little bit of this in the first one, but just for review, since it's on the slides. So, no matter what you're going to do with radio, at some point you got to send out a signal, and you send it out through an antenna. I see there's some walkie-talkies in the back. The antenna is the long wire sticking out the top. What the antenna does, you send a current through the antenna, and that transforms that into a radio wave that's sent out. And then, if you want to receive, it takes the radio wave and transfers that into a current. And the radio can then do stuff with the current.
Now, can anyone tell me how a single piece of wire can conduct electricity? I mean, he's talking about a current, but this is just one piece of wire in the air. What's going on here?
Some funky magic that you get into, like in EMAG 2.
Yeah.
Witchcraft.
Yes.
Is it because it's being converted into radio frequency?
Well, how is it getting? Okay, I mean you're onto something. We're talking radio frequencies, right? This is not direct current. This is not like hooking a battery up to a piece of wire and having it,
Well, if you have a magnetic field, won't it induce a current in the wire? Like
Yes.
if there's some kind of magnetic field.
Yep. But what's special about that magnetic field? If I stick a magnet up to my antenna, am I going to get a
It
current?
has to be changing.
Has to be changing. Exactly. So we're talking about alternating currents to get energy out of an antenna, and that's the trick. They can't be direct current. So
So yes,
just want to
antennas.
make that.
Yeah, antennas are magic. If you want to learn more about antennas,
Talk
you're
about a
welcome.
giant air core transformer, that's what you got here.
Yeah. Okay. Well, so that's the antenna. To connect your radio to your antenna, use something called a feed line. In the case of a walkie-talkie, there's hardly any feed line. I mean, they're like right next to each other. But if you're going to have like a big tower out in the middle of a cornfield, you're probably going to have a feed line running back to your house. And then you'll need some equipment. Usually when you put up an antenna, it doesn't work right away, so you need some equipment to see if it's going to work or not. Because it's very important that your antenna works correctly. Otherwise, something will blow up depending on what's the weakest link. So you do not want stuff to blow up.
Great big carbon tracks inside
Yeah.
the radio.
It will ruin your day.
And your radio. And your wallet.
So if you were going to look at a antenna such as the one on the walkie-talkie, we call the wire itself, which is what's in the middle of the antenna, the element. Okay, there can be multiple elements in an antenna, but in a walkie-talkie case, there's only one element. We call it the driven element because that's the one that we put current through. And if there's multiple other elements on the antenna itself, we call that an antenna array. And those other elements that are not driven can actually help your antenna performance, believe it or not.
Who's ever seen one of these type of antennas before?
You got TV in the 90s.
Yeah.
Yeah. So only one of those wires, I think it's the longest one, is the driven element, and all the other ones are what we call parasitic elements.
If you're trying to draw a Yagi, then what the undriven one should be, the back undriven one.
Okay.
Yeah. I was just doing.
The parasitic one in the back should be longer than the driven one
This is the
Like-
reflector.
by very small amounts of a wavelength.
Yeah.
You won't have to do it for this class, but look up Yagi design. You can get
Yeah.
all the figures out.
But we call this the reflector, the driven element, and the parasitic.
Yes. So, preferably, you want your antenna to be resonant. And we talked about resonant a few, like 20 minutes ago or something. Resonant means there's no reactance, there's only resistance. So there's zero reactance, and that's good if your antenna has 0 reactors. That means it's like the maximum effectiveness, maximum efficiency. The feed point is where, I guess, physically you plug in your radio. It's just like the feed point for a walkie-talkie would be where you screw in the antenna, I guess.
One of the simplest antennas is a dipole. And that just means it has 2 elements, and the feed point is at the very center. And we typically have our feed line go right up to the top. Like so.
What's on the walkie-talkie is what's called a monopole, which is only one pole in the feed point. You just chop off half the dipole. Radiation.
I'll cover this.
Oh, you want to cover radiation?
Yeah. Whenever someone says radiation, don't we all think of radioactivity? Of course, I do. You know, Fukushima and
Uranium.
uranium and plutonium and whatever. They are related in that they all have energy. The difference is radioactivity, we're talking about ionizing radiation, which means the energy is high enough such that it can split apart atoms and get ions and whatnot. And that's ionizing radiation. Non-ionizing radiation is what we talk to each other with our cell phones. It's radio waves, electromagnetic. Non-ionizing radio waves.
So how this, if you could see a radio wave, you wouldn't actually see one thing. There's actually 2 waves going. One wave is traveling, maybe I get in the camera with this. One wave is traveling like this, and the other wave is snaking like this. And one of the waves is an electric wave, and the other wave is a magnetic wave. And they're at right angles to each other, traveling. How do I do this? Like
It's
this.
like this type thing.
Yeah, some voodoo
That was
magic.
really hard to do.
Yeah.
Can you draw in 3 dimensions on a conventional board a little better than I can?
So one's going up and down, the other one's going like in and out, but they're both traveling the same direction, and they're both at the frequency that I guess your radio is at, or whatever your transmitter is at. So one thing that's important is the orientation of the waves themselves. So normally, what we call a vertically polarized wave is one where the electric field is like this, and the electric field.
Do you need a second arm to like?
Man, I need
Can
like
you do
5
this?
arms.
Okay.
And then the electric field's like this, and the magnetic
I
field
gotcha.
is
I'll do
like-
this one.
okay. This is all right. And then the horizontal is the opposite of that, where the electric field is in and out, and the magnetic field is up and down. There can also kind of travel in a circle where halfway through it flips and travels in a circle. Anyway, that's more complicated than I want to get into. But it's important that if your antenna is putting out a vertically polarized wave, it's important that the other antenna on the receiving end is also vertically polarized. Otherwise, you won't be able to talk to each other. It's like both the waves have to hit like this. If one hits like this, or like this, it's not gonna like.
There are several questions on the exam about polarization.
I think the figure is something like 20 dB.
Yeah.
Yeah.
You lose a lot.
Yeah. So if your buddy in a field has a walkie-talkie held to its side, and you have your walkie-talkie, I guess, up to your face like this, you won't be able to talk to each other for very far. I mean, you probably do it in this room, but if you guys turned it the same direction, you'd be able to talk much farther.
When we communicate with satellites, circular polarization is pretty common. Basically, just point your antenna at it, and it'll magically work. We have cross-polarized antennas that have both polarized and the same. Anyways, there are many
Anyway.
questions you can go through the practice test. This will just familiarize yourself with the concept.
Yeah, so that cross polarization happens when they're not polarized in the same direction. It's very important that they are. If they're not, you'll reduce your signal by a factor of 100, which is 20 dB, by the way. Okay. Speaking
What
of
is dB?
yeah, speaking of dB,
Remember when I said we actually do use deci a little bit? Well, here it is.
well, all you have to know for decibels is they're an easy way to multiply numbers without actually having to multiply. Instead of multiplying, instead of you multiply like 100 by a million, that's 100 million. What we could do is say, well, that's 20 dB plus 60 dB. Is that a million? 60 dB? 20 plus 60 is 80. Boom, there you go, 80 dB. Yes?
Can you talk a little bit about circularization?
Circular polarization?
Not just polarization in the context of, let's say, simple Yagi antennas.
So
Let's say,
if you have a Yagi antenna, I wish I could show this better, but I don't.
Yeah, I would say the easiest way to the take-home point here is if I have a Yagi that's horizontal and someone else has a Yagi that's vertical, it's not going to be near as effective as if both of them are horizontal or both are vertical.
so both have to be.
They need to be polarized the same. So, has anyone messed with polarizers in your sunglasses or something? Have you ever taken sunglasses and put them together and rotated them, or looked at an LCD with polarized sunglasses? You'll see that it gets real dark and then it gets lighter, gets dark again. That's because polarization is going to be cross-polarized when you can't see it and in the same plane when you can. Same exact way with an antenna.
If you have this Yagi, would it matter what polarization the
So that what you're talking about is actually secretly two Yagis. One, the arrays are pointed in this direction. The others are pointed in this direction. It's actually, you're driving two antennas at the same time.
And that will eliminate the need for polarization. That's what we use to talk to satellites with, because the satellite could be just tumbling and it's polarized all over the place. But when you have the two Yagis that are vertical and horizontal, it doesn't matter. It'll be effective no matter which way. It just kind of,
To do that takes advantage of the speed of light and coax.
Yes,
You
you phase
actually
them.
use a special harness on that to get the circular polarization you need. And in fact, if you have one that's crossed, sometimes you will find somebody who's wired it up with a simple switch. So he can have either vertical or horizontal and only has to pay for one rotator. Okay. And the feature is typically mobile stations like me, I use vertical polarization. The repeater uses vertical polarization because so it hears me better and you can hear it better. Point to point, if you notice the antenna on the top of Broom Hall on the tower, it's horizontally polarized. Fixed stations tend to use horizontal polarization, even on 2 meters. Even on 2 meters when not talking to a mobile station.
Okay, back to decibels. How you would, I hope it says this on the next slide. No, okay. Well, to transfer between like a regular number and a decibel, what you would do, I don't have,
I gotcha.
okay. It didn't make
It
that
almost
work.
made it.
What you would do is you would say your decibel is, I hope, is equal to 10 times log, and log is logarithm,
Base 10,
base 10.
not the natural log.
If you don't know what logs are, there's you can get a calculator that'll do logs for you. But log of whatever number you have. So if this was 100, log base 10 of 100 is 2.
Because 10 to the 2 is
100.
Okay. If you look at this, you may see a pattern in the number of zeros.
Yeah.
That's intentional. They did that, so it makes sense.
So the 10 out front is just a scale factor. That just says if you have a number if your number is 10, that means your dB is also 10. That's just a handy thing. You only use 10 if you're working with power, which is measured in watts. If you're working in voltages or currents, you have a 20 here. And that's so all the calculations
You can
work out.
derive that.
Yeah. We're not going to go do it. Use 10 log number for power and 20 log power for, or 20 log voltage for voltage or current. Okay. Decibels are important because they measure how good your antenna is. So the antenna, you're able to, it sort of amplifies your signal in a certain direction. So typically you'll buy an antenna that says, oh, we can give you 10 dB of gain, which means it amplifies your signal 10 times. Versus if you had just used an antenna that only has, it radiates equally in all directions. That's what we call a omnidirectional antenna. Thank you. But if your antenna has gain, it probably points in a direction.
Okay, what's the difference between isotropic and omnidirectional? Isotropic means, well, first of all, isotropic is impossible. We can't really get an isotropic antenna. That would be a point source of RF energy that radiates like a sphere. Whereas omnidirectional would be like this monopole we're talking about on a little handy-talkie. It radiates outward, but it's not so good going down, and it may not be so good going directly up, but it does pretty well going outwards in all outwardly directions other than top and bottom.
And how we visualize that is something called the antenna pattern. So if you kind of wrap your head around, if the antenna was sticking straight out of the board like this, it would radiate better in this direction because the graph is bigger in that direction. It doesn't do hardly anything at all back in this direction. It has some radiation back off the back corners. But this would be a directional antenna because it radiates mostly in that direction. And these numbers are all plotted in dB.
Yeah, and this is azimuth, so this is only showing horizontal. This shows nothing about how great it goes going straight up or straight down. That would be elevation. You can also plot these three-dimensionally on a computer, and it looks really awesome because then you can see exactly how much energy is going into the sky, for instance, if you're going to talk to satellites.
So if you're looking at this graph and
I'm
you
gonna draw
want,
one so we can.
you're going to draw one, okay. And you want to name some points on this graph if you're going to talk to your antenna buddy. You want to say, if you have a null
Draw that same one.
somewhere on a graph, that means you have minimum gain in that direction. For example, the back lobe of the radiation pattern I just showed you had a null because it
Basically, is not irradiating much at all.
Yeah. If you have a lobe, that's an area where it radiates some, I guess, electromagnetic field. Your main lobe is the one where it's highest, and your side lobes are the ones where they're kind of okay. And what we designate as the forward gain, we call, it's a measure of how big that main lobe is. And that's the one we really care about. We don't really care about how big the side lobes are.
Now, if we go back, we can actually look at what is the forward gain of this particular antenna. Looks like it's 0 dB. And how much is 0 dB in terms of actual power gain? So if we say dB is 10 times the log of the number, then we've got to say, well, let's see, it would be 1. There is no gain. But there's also no loss. So this is a passive antenna. If you see, you know, basically we can end up getting more than this. We could have antennas that put a lot more power in one particular direction. This may be normalized, or maybe this is just a. There are lots of reasons why it might be zero there, but that's
Another thing you need to point out is the guy over there can't hear it.
yes.
If you're outside that loop, they're not
If
getting your
you're
signal.
if you're pointing in the complete opposite direction of this person, your best bet of talking to him would be rotating the antenna or hope that it goes all the way around the Earth and then back to him, because you're really not getting much energy out this way.
On the other hand, if you want to ignore that guy,
Yeah, you don't like that guy.
yeah.
Yeah. So that's some of the radiation pattern vocabulary that we just talked about. The graph that we showed you was the azimuthal. How was it there? The azimuthal pattern, which just means the pattern looking around the antenna. The elevation pattern would be the pattern if you were looking like this way-ish. But the important one, I would say more is the azimuthal pattern, because you're looking at,
Depends on what you want to do.
well, yeah,
Depends on what you want to do. If you want to talk to a satellite with that handy doggy, probably care more about the elevation. If you want to talk to your neighbor, probably more about azimuth. So it just depends.
Oh, how about this? Yeah, so the azimuthal pattern is on the left, and that's measuring like around the antenna this way. The elevation pattern is if I stuck the antenna right here, this would say, hey, this antenna radiates a lot up towards the sky and a lot up in this direction and this direction, but it doesn't do anything like down below it, which is handy.
But it's kind of impossible for it to do that, because you've got this thing called Earth. You've got a ground plane here, and it's not going to really allow you to get any sort of gain into the ground. It's defined to be zero.
So I hope everybody can visualize that. So another measure of the antenna is the front to back ratio, and that's a measure of how powerful your antenna is in the strongest direction versus how weak it is in the opposite direction. So the ratio up here is 0 dB, and this point way back here is like minus 40 dB. So its front to back ratio would be 40 dB, which is pretty good.
Now, if it were an omnidirectional antenna, what would the front to back ratio be?
There's no front, there's no
Or
back.
0 dB?
Front to side ratio is just the measure of the main lobe to the directions at right angles to the main lobe. So it would be this minus whatever this value is, and that's like minus 3 or 4. So there's then a front to side ratio of like 3 dB. All right. Okay, so that's the antenna. Now we're working our way down, and now we're at the feed line. The feed line, once again, is what you connect from your radio to your antenna. Its purpose is to get the RF energy that's generated by your radio to the antenna. There are two basic types. One's called coax. Coax is short for coaxial cable. And what that is there's one wire in the center of coax, and there's like an outer sheath of wire, like a metal shield around it. Braid, is that the okay? There's a metal braid around the center conductor, and they're separated by a dielectric. There's also another one called open wire line, also called ladder line, because if you stretch it out, it looks like a ladder. And that's what they used back in the day. If you're at your grandpa's house,
You might take some regular old copper wire and make some yourself by getting like wooden dowels back in the day and taping them to the wooden dowel.
Field day antenna is a wire line.
Have one of these in my trunk.
so the wires are actually the side the side ones going up, and the center, I guess, green things just keep them from touching.
It's usually plastic, the middle part.
Yeah.
Or dowels.
So feed line is not perfect. There's usually, if you use feed line, there's going to be some power that's lost in the feed line itself, unfortunately. And that increases with your frequency. So if you're using a feed line at like 1 megahertz or 2 megahertz, you might not have a lot of loss. But if you moved it to 200 megahertz, you could have like a whole bunch of loss for the same cable. Once again, this is a coax cable. This is the center wire, and this is the metal braid that's around it. And they're separated by dielectric, and usually they put, every time they put an outer insulation, you don't want to be touching it while it's hot.
They also, like for big radio stations, broadcast stations, they use something called hardline, which is very rigid, can't really bend it. When you do have to bend it, it's got this huge bend radius to it. But it uses air inside, which is a much better dielectric than the foam that you would probably see inside, like RG58. That's a type of coax that's commonly used for television and your cable internet or whatever. So.
This is open wire line, also called ladder line, twin lead, whatever you want to call it. It's just 2 wires running parallel for some distance. Some differences between coax and open wire line and their performance. Open wire line generally has less loss than the equivalent run in coax. It's lighter, but it's more difficult to use because coax is not affected by other things near it, while open wire line is. So you have to be careful about what's near your wire while you're using it.
The twin lead here, really commonly used for really old televisions. You may find it in an old house still, but most of that's been replaced by 75 ohm coax.
Yeah. And if you were to use open wire line, because you want to, you would probably have to use some sort of impedance matching network, because your radio is generally meant to use coax. Has to use as a socket for coax and not for open wire line. You can't just replace the two. They're not interchangeable. So you have to use an impedance matching network with most radios. The characteristic impedance of a feed line is very important, because your radio is generally meant for 50 ohms, a 50 ohm impedance. And coax is already 50 ohms, or 75 ohms. So the ones you would use are 50 ohms, so you can just plug it straight in. If you're going to use open wire line, that's usually 300 ohms or 450 ohms or 600 ohms. And if those are not, if your radio and your feed line are not matched, then you'll blow something up. Horrible things will happen. So it's very important that whatever feed line you use is matched to your radio.
Or your radio is smart enough and says, I'm going to reduce power so I don't destroy myself.
That's a smart one. Not all of them have that, so be careful.
What's the significance of the structure of the cable? The structure of the conductor?
The conductors themselves.
Right. It's electricity again flowing through. So what's the significance of having a coax or a...
So the calculation of characteristic impedance is what we call a high frequency calculation. So normally if you're at DC, they're just wires. But wires aren't wires when you move up to high frequencies, such as ones where you would be operating your radio. You would have to take into account there's some resistance in the wire. No wire's perfect. Most wires are perfect. Cal's about to correct me. You also have to take into account there's some leaky capacitance and some leaky inductance that you have to take into account. And those are difficult calculations. But for a certain geometrical length of, or geometrical cross section of wire per se, you can calculate that, and it's going to be the same throughout the wire. I don't want to get too deep into it because we'll be here for like another 2 semesters. So that's all I'm going to say about it. If you want to look up characteristic impedance on Wikipedia, it has the formulas and why it's important.
Just to show you, this is what twin lead looks like schematically. We call this the lump sum model. It's just a bunch of inductors and capacitors. You can imagine if you have 2 long wires running close to each other, you have capacitance between the wires. And any wire has inductance, especially if it's really long. So we can basically chop this into little tiny pieces drawn here as inductors and capacitors. And you can definitely learn more about that than we would ever have time here. But that's kind of how we start looking at what transmission lines do at high frequencies.
So it's important that the feed line you're using is matched to the radio that you're using. If it's not, once you send out a radio wave and it hits the feed line, like at some point your radio hits the feed line, some of that power is going to be reflected back into your radio, which is very bad. Ideally, you would have no power reflected. That would be if they were matched perfectly. But we can measure that level of reflection by something called the standing wave ratio. And so when you send out your radio signal, it has a certain amplitude, and the reflected value has some sort of amplitude, and the measure of those is your standing wave ratio. I hope I'm getting that right.
Basically, here's what you need to know. 1 to 1 is a perfect match.
That doesn't happen.
Well, it can happen, but it's more commonly you'd see it maybe 1.2, 1.3 to 1. 2 to 1 is still marginal. 3 to 1, 5 to 1, 10 to 1, those are really bad matches, and you probably need to do something about it, like get an antenna tuner.
And we can measure that with some fancy equipment called an SWR meter. And there's SWR. Or an
I'm
SWR.
working on that presentation now.
The what?
I'm working on that presentation now.
Oh, good.
Float around.
Okay, right. So the more it bounces back and forth, the more power you're losing. That's less power that's getting to your antenna, less power you're transmitting. Bad. Once again, SWR is best when it's 1 to 1. So you have a 50 ohm radio with a 50 ohm feed line. That's the best. 1 to 1's perfect. You could usually operate if it's 2 to 1, but anything higher than that, you really want to not. Such as 3 to 1, don't do that. If you have high SWR, there's some things you can do to fix it, such as, SWR mismatch can also exist between the antenna and the feed line, which is usually what happens. You're usually going to use a 50 ohm radio with a 50 ohm feed line, but your antenna might not be 50 ohms. So there's also going to be some reflections there, but you can tune your antenna by adjusting like the length or the height or whatever. You can also just get a fancy box called a antenna tuner, which will sit in between your radio and your feed line, so that way your radio will always see 50 ohms no matter what, and the antenna tuner, that little box, will take care of any reflections that might occur.
Now, the other thing is you can also change the frequency, because sometimes you might operate an antenna at like 146 megahertz. You've got a 3 to 1, but you operate at 144 something, and it's 1.2 to 1. And that's just because that particular antenna has particular characteristics that are different at different frequencies. So not all antennas are created equal, and not all antennas have infinite bandwidth that we can operate at the same antenna at 100 megahertz and expect it to have the same characteristics at 200 megahertz, for instance. So,
So if you have an SWR meter, you're able to quantify how good your antenna is doing. You're able to see if whatever change you make helps the SWR go down or makes it go up. So usually, when you're testing your radios, you don't use a actual antenna because if you're testing and something goes wrong, that means you emit a radio signal accidentally, and the FCC doesn't like that. So what you do is instead of an antenna, you use what's called a dummy load. And all a dummy load is, it's a
big resistor.
It's a big 50 ohm resistor, so it's going to look like 50 ohms. So your radio will be happy, and it can dissipate a lot of heat. So if your radio can put out 100 watts, that 50 ohm dummy load has to be able to dissipate 100 watts of power as heat. Yeah, so it helps you troubleshoot without actually getting on the air. So we were supposed to bring samples with us, apparently. Did you forget to take the slide out?
I don't know what happened here, maybe this is the notes pages.
Okay.
Yeah.
Yes, this is the notes pages.
All right.
Okay.
You're done.
Yay! I'll make sure. Yay! All right. Cool. We're only half an hour late.
Well, we covered
You might
three
actually
hours.
get through all of the presentations next.
Yeah. That's, yeah.
We covered 3 hours and an hour and a half. I think that's pretty good.
Literally.
So are we giving the test at the end of the next meeting?
Yes.
Okay.
If
I will let you.
everyone's okay with that. So for the next meeting, which is gonna be same time, same place next Monday, if everybody can bring a driver's license, and if you've got $15 cash is preferable to take the test. We don't keep that money; it goes to the ARRL, and it covers their testing fees and all of that. But you'll have to have a driver's license, some sort of a photo ID, and yeah, we'll run through the last bit of the slides, and then if you're ready, you can take the test.
You can bring a 4-function calculator. Can't have memory. Can't be programmable. Whatever. Can't graph.
Yeah.
We also have some.
That's
You
what I was
don't
just
have
gonna bring them.
You may use it. You may not. Just depends on what questions are on there. But like we talked about last week, the 300 divided by frequency in megahertz gets you the wavelength in meters. That is a very useful thing. But again, if they say 150 megahertz, they want you to name what band it's in.
2 meter band.
So none of the calculations require a calculator. You could
That's right.
you could do them
all
by
on-
hand. None of them are like really hard, but I mean, you can bring a calculator. Why not? So
Bring pencils.
Oh yeah, bring a pencil. And it'll be so plan to stay a little bit longer. The test is only 35 questions.
How many hours are we going to
So-
cover in lecture?
That I don't know. We'll probably have like this, like a class that's about an hour to an
We'll
hour
try
and
and keep
20.
it a little on the shorter side.
And then yeah, the test usually takes most people no more than a half hour. Like that's absolute worst case because it's 35 questions, but a lot of them you'll look at it and be like, what unit did you use to measure resistance? Oh, okay. So a lot of them it's gonna be like look at it, read it, mark it. That's all there is to it. So go ahead and study up.
what are we going to cover the next time? What are the next hours?
Yeah, I just turned the computer off.
Okay. Well, I know for a fact we have not covered rules and regs
Yeah, so
yet.
yeah,
We haven't covered rules and regs, we haven't covered safety.
Okay.
So no offense, but the boring
We
parts.
haven't covered, basically the hand band layout yet.
Okay.
I think that's about, those are the major ones, I'm pretty sure.
Should we send that information, the slides, before the next meeting so they have it?
I have to get with my
Okay.
head together and crank
Yes.
them out.
Okay. Okay.
In the meantime, though, if
I'm
you go
always
take the
step
practice
ahead of
exam, if you go take the practice
Who
exam,
has
you'll
not
cover
been
everything.
to hamstudy.org yet?
Or another
Or
studying
another
type
site,
thing, yeah.
hamstudy.org is my
Or
favorite.
Zen or any one of the other ones.
If you go
Yeah.
on there and take the practice test a few times, and if you're getting consistently,
It takes 77% to pass, so if you're
over
consistently
77%?
passing, you're probably good. So, yeah.
The worst problem is the rules and regs and some of the other stuff, so, you know, if you're a double E major, you probably got most of the technical stuff down. The rules, I mean, face it, this is a government organization that's doing this, so they have rules, and they don't have to make sense. Government rules don't make sense necessarily. Just the way that works. They're written, some of them are written by politicians.